Hello everyone, welcome to Civil Galaxy. I am Dr. Pruthviraj B S. Today we shall see how to analyze a propped cantilever beam with the help of consistent deformation method. If you consider this beam here, at the free end of point B, we are having a rigid support. A rigid support at point B which is 10 millimeters below the free end. Similarly, we have got EI value as 15,000 kilonewton meter square. So, to analyze this beam with the help of consistent deformation method, our first step is to find the degree of static indeterminacy. To find out the degree of static indeterminacy, we need to have the number of reactions and the number of available equilibrium equations. So in this particular beam, if we consider the number of reactions, we are having one vertical reaction about point A. Since there is no horizontal forces, the horizontal forces along point A is 0. We are having one moment about point A. Similarly, we are having one vertical reaction here about point B. So now we are having total number of reactions 3 and number of available equilibrium equations are 2. So the degree of static indeterminacy will be equal to 1. Means this one force or one extra force needs to be treated as a redundant force. So in step 2, if we go for step 2, we need to consider any one forces out of these 3 forces to make the structure determinate for the further analysis. So here we are let us consider the reaction about point B in the vertical direction as the redundant force. So if we consider the vertical reaction about point B in the vertical direction as the redundant force, the same propped cantilever beam can be treated as a cantilever beam. This is point A, this is point D, carrying a point load of 40 kilonewton. At point C, a point load of 60 kilonewton. This is point B. So from B to C distance is 2 meters, C to D distance is 2 meters. Similarly, D to A distance is 2 meters. So now I have to find out the downward deflection at point B due to the applied loading, due to applied loading or external loading, we will consider it as capital M. Similarly, we need to find out the downward deflection at point B, due to applied unit load. So to find out the downward deflection of this particular beam about point B, we need to consider the unit load method. In the unit load method, we know that whenever we want to find out a deflection at a particular point, we need to apply a unit load. So here we need to find out deflection about point B. We will apply a unit load about point B. This is point D, point C. This is 2 meters. This is point B. This is 2 meters. This is 2 meters. This is point A. So now to further analyze this problem, let us consider a table to simplify. So if we closely observe this beam, we are having three portions, that is BC, CD and DA. So we will take each individual portion separately. We are having portion that is coming from the right side, BC, CD and DA. So for this particular portion, we need to consider the origin. So here the origin for portion BC will be B. Similarly for C to D, the origin will be C. For the portion D to A, the origin is D. So for this particular portion, we need to apply the limits, that is the distance. For portion B to C, it is 0 to 2, CD it is 0 to 2, similarly D to A it is 0 to 2. So for this particular portion, for this particular beam, each portion we have to consider the capital M, that is moment due to external loading. Similarly, we have to consider small m, that is moment due to applied unit load, and we are having flexural rigidity EI. So for each portion EI here. So now to further find out the moment due to applied or due to the external loading, for this portion BC, if I consider a portion here, a section x at a distance of x from the origin, I want moment about this point. So force multiplied by perpendicular distance rotates in the clockwise direction, creating a hogging moment. Since there is no load at the portion B to C, the moment will be equal to 0. Now if we take a portion C to D, similarly we will take one section and a distance of x from the origin C. We want moment about this point. So force multiplied by perpendicular distance, force here is 60 multiplied by perpendicular distance is x, rotates in the clockwise direction, creating a hogging moment, which will be equal to 60 into x negative, since it creates a hogging moment. Similarly, for the portion D to A, considering a section XX at a distance of x from the origin D, we want moment about this point, force multiplied by perpendicular distance, force here is 60 multiplied by perpendicular distance from C to D, it is 2 plus x, rotates clockwise, creating a hogging moment which is negative. Similarly, we are having one more force multiplied by perpendicular distance, 40 into x, which is negative. Similarly, now we have to find out moment due to the applied unit load. For the portion B to C, if we consider a section x here, a distance of x from the origin, we want moment about this point, force multiplied by perpendicular distance, which is minus 1 into x. Similarly, for the portion C to D, if we consider a section x here at a distance of x, here about this point, force multiplied by perpendicular distance, force here is 1 kilonewton, distance here is the portion 2 plus x, so it is minus 1 into 2 plus x. Similarly, for the portion D to A, here it is x, the distance is x from the origin D. Similarly, it will be minus 1 into 4 plus x. So now, to further simplify the problem, we need to find out the deflection about point B. The objective here is to find out the deflection about point B. So for that, by using Castiglione's second theorem, we have deflection which will be equal to 0 to L, capital M into small m divided by EI into dx. We need to find out a deflection about point B. So deflection about point B will be equal to deflection in the three portions, that is from B to C plus deflection about C to D plus deflection about D to A. So we have to find out the deflection for each individual portions. So for that we will consider delta deflection in the portion B to C first. That is, if we take the formula 0 to L capital M into small m divided by EI into dx, here capital M for this portion is 0, small m is minus 1 into x, so this comes out to be 0, which is delta BC is 0. The value of the deflection in the portion B to C is 0. Similarly, we need to find out the deflection about point or the portion C to D, which is 0 to L capital M into small m divided by EI into dx. So now if we consider this value here for the portion C to D, m is minus 60 into x. Similarly, small m here is minus 2 minus x. So now if we simplify this one, this will be equal to 120 plus 120 plus 60 x square. 120 plus, sorry, this is 120x plus 60x square. A limit here is 0 to 2 by EI into dx. Here also limit is from 0 to 2 divided by EI into dx. So now if you further simplify this value, we are having 1 by EI. If we take outside this one, integrating 120x square by 2 plus 60x cube by 3. The limit here is 0 to 2. So now upon further simplifying, the deflection about point C to D will be equal to 400 by EI. 400 by EI. Now similarly finding out the deflection about point D to A. So the limit here is 0 to 2. Applying the value of these two portions, that is capital M and small m about the portion D to A, we are having, we'll take it 0 to 2, that is, we'll write here, sorry, first then we'll go for the answer, minus 60 into 2 plus x minus 40 into x, minus 40 into x, minus 4 minus x. On further simplifying, we have 480 plus 240x plus 160x, 160x plus 120x plus 60x square plus 40x square divided by EI into dx. So now the deflection in the portion D to A, delta dA, the final answer will be 2267.67 by EI. We need to find out the value of delta B, which is deflection about portion B to C plus deflection in the portion C to D plus deflection in the portion D to A. Deflection in the portion B to C is 0. Deflection in the portion C to D was 400 by EI plus deflection in the portion D to A is 2267.67 by EI. Now the deflection about point B here will be equal to 2667.67 divided by EI. The value of EI is known here, which is 15,000 kilonewton meter square. Upon further simplifying, the deflection about point B will be equal to 0.017 meters. Since we are having a rigid support here which is 10 millimeter below, so we will consider that as delta dash B. So this deflection about point B is 0.017 meter. If we convert this in terms of millimeter, will be 17 millimeter minus the support which is 10 millimeter below the point B will be minus 10 in the downward direction. So this deflection about point B will be equal to 7 millimeters. 7 millimeters, or we can call it as 7 into 10 raised to minus 3 meter. Minus 3 meters. So now taking step 3. In step 3, we need to find out the upward deflection. We need to find out the upward deflection. We need to find out the upward deflection due to reaction about point B in the vertical direction. For that, we will consider the given beam here. This is point A. This is point D, a distance of 2 meters. This is point C, distance of 2 meters. This is point B here, distance of 2 meters. This is vertical reaction about point B. So if we now want to find out the upward deflection about point B here, we will consider this as YB. So now, if you want to find out the deflection, upward deflection due to the reaction about point B in the vertical direction, we know from the standard deflection equation, whenever a cantilever beam is subjected to a point load at the free end, the formula is WL cube by 3EI. Since W here is reaction about point B in the vertical direction, L, the total length is 6 cube divided by 3EI. So now my vertical reaction about point B will be equal to 72 reaction about point B in the vertical direction divided by 3EI. So if we further simplify this by putting the value of EI, it is 15,000 kilonewton meter square. We are having 4.8 into 10 raised to minus 4 reaction about point B in the vertical direction. Let us consider this equation as equation number 2. Our equation number 1 was the deflection about point B, which is delta dash B, which was 7 millimeter or 7 into 10 raised to minus 3 meters. This was our equation number 1. So fourth step in the analysis will be to apply the compatibility equations as per the consistent deformation method, which is equation 1 will be equal to equation 2. So your equation 1 is 7 into 10 raised to minus 3, that is delta dash B should be equal to YB, which will be equal to 4.8 into 10 raised to minus 4 reaction about point B in the vertical direction. So if we simplify this further, the reaction about point B in the vertical direction will be equal to 16.20 kilonewton. So out of these 3 unknown forces, we have got one reaction or one unknown parameter. Similarly, we need to find out other 2, reaction about point A in the vertical direction and moment about point A. So for finding out the reaction about point A in the vertical direction, we will consider summation of all the vertical forces will be equal to 0, RAV plus RBV, which will be equal to the total load 40 plus 60, 100 kilonewton. So RAV plus 16.20 will be equal to 100. So reaction about point A in the vertical direction will be equal to 83.80 kilonewton. So we have got another unknown parameter. The last unknown parameter in this analysis will be to find out the moment about point A. So to find out moment about point A, here, we want moment about point A here. So force multiplied by perpendicular distance, that is RBV, multiplied by perpendicular distance is 6, which rotates anti-clockwise, creating a sagging moment, positive, minus 40 into 2 minus 60 into 4. So applying the value of RBV, which we have got here, 16.20, moment about A will be equal to minus 222.8 kilonewton meters. So now, to summarize this problem, we were initially having 3 reactions. We had to find out the 3 unknown parameters. So the vertical reaction about point A is 83.80 kilonewton, which is in the upward direction. Similarly, reaction about point B in the vertical direction, which is 16.20 kilonewton in the vertical direction. Similarly, we are having moment about point A, which is equal to minus 222.8 kilonewton meter, rotating in the anti-clockwise directions. So this is the total value of the analysis of this proper cantilever